We have tried everything to make paramotor propellers better. In this video, I will guide you through 10 different experiments and research projects that we did in the last 10 years. Everything on an aircraft must have a reason. Ignore the status quo, imagine from scratch, and build what you can justify with science. Fail 5 times to succeed once. This is how we innovate paramotors, and for you, understanding the science behind will make you a smarter pilot. If you deliver 25 horsepower from the engine onto the propeller, what the prop will do will split those 25 horsepower into 2 different forces. The lift of the wing will somehow translate into the thrust of the propeller, and the drag of the wing will translate into the torque of the propeller. So the quest for the best propeller is basically to reduce the drag and the torque component of the prop and increase the lift and thrust component of the prop, more efficiently converting the horsepower into thrust. Now, it's a very complicated process. So to simplify the whole stuff, it's diameter times number of blades of the propeller times the type of profile, the profile length, and the profile pitch, and that all will somehow result into the RPM that the engine will be revving. 10 years ago or so, 125 was the industry standard. All paramotors were 125, and we have built our paramotor around a 132 centimeters long propeller, simply because longer is better. I made a very detailed video in the paramotor geometry classroom series where I explained the math and the physics behind why a 132 propeller is better than a 125. Since then, the 130 centimeters prop seems to become the industry standard, and most paramotor manufacturers are using 130 as their go-to propeller. Some are even experimenting with 140 on 150. We tried 140 with the Enduro cage, is perfectly doable and delivers great results. 150 seems to be kind of out of the practical range simply because of the size of the cage. Now, 130 centimeter propellers from different manufacturers, if you compare them, they seem to perform very similar. I have a lot of experience with the Scout propeller, with Helix propellers and E-prop propellers primarily. And I can say they all perform pretty much the same. Now, we did not give up, and we kept trying to find the best ideal propeller, and we tried everything. As the first thing, we tried the 3 blades. I don't have the propeller with me here. The only thing I have left of that propeller are 2 photos from the old times. I wasn't really recording that for video. I was only doing the experiments and measurements for our purposes, for the research and development. Now, the 3-blade prop didn't bring any benefits. It didn't have more power, like more thrust. It wasn't more efficient at cruise. It wasn't quieter or louder, but it had a different sound. Now, the sound was the only benefit I could identify. It was a different pitch. It sounded like a MotoGP racing motorcycle. It's like an amazing sound. I loved it. But other than that, it was obviously more expensive because you have 3 blades instead of 2. It's more difficult to repair and balance, and it's heavier in mass, so it takes a little longer to spin up. Practically and theoretically, the 3-blade propeller is no better than 2-blade. Actually, there is some research out there showing and proving that the ideal prop would be the 1-blade prop. It's just difficult for balancing, and it puts a lot of like excessive load and wear on the bearing, so it's not a very practical solution. So I believe that we will stick with the 2 blades for now on. The white tip project. This big fat propeller with the white tips was our first propeller that we designed in-house, and it's a very special one. And to explain the theory behind this prop, we need to go back a little bit. Now, the power curve of the Variomatic master is not a public information, but I guess it looks like the power curve of any other engine out there, where you can see that the peak power is actually not at the maximum RPM, but slightly earlier. And this seems to be confirmed by the official Variomatic website, which states that the Variomatic Master Plus is having the peak power of 25 horsepower at 7,800 RPM, although the max RPM is 8,600. It means when we are at full throttle, we are not at the full power of the engine. So the propeller is not applying sufficient resistance on the engine, and it allows it to rev past the peak power point to 8,600 RPM. Now I was thinking, yeah, maybe we could do better. Maybe we could design a propeller that is larger and puts more load on the engine. It will stop the engine at 7,800 RPM, so we can actually use the maximum power of the engine. We would gain more thrust, better climb rate, and so on. So we designed this fat boy. Very wide blades. It's actually 12.5 degrees pitch, measured at the 75% of the diameter. So it's much larger, big fat blade at a higher pitch than normal, and it effectively stops the engine at 7,800 RPM. So the results were amazing. I had lower RPM at cruise and better fuel economy, and I had a very good climb rate. So with this big fat propeller, I had better climb rate at 7,800 RPM than I had with a normal propeller at 8,600 for a short period of time, unfortunately. I've noticed after 40-60 seconds, which is a very short time, the peak RPM started to drop and it wasn't delivering the power anymore. I believe the reason behind might be that using the full power of the engine produced so much heat that the engine wasn't able to cool anymore, and I assume the piston rings expanded a little bit, increased friction in the whole engine, and the RPM started to drop. So great propeller for cross-country flying if you don't need to climb at full power for too long. So after realizing that, we stopped the production of this propeller and we switched to a design with a smaller blade, smaller pitch. And that, just like everybody else is doing, that will allow the engine to rev up past the 7,800 peak power to 8,600. So we are effectively flying at less horsepower than the engine is capable of. Don't blame Variomatic, don't blame Helix or eProp. All other engine manufacturers are doing the same. This was really fun. So we still kept trying and searching for a better propeller and improve the efficiency and thrust of the propeller. And then Milos joined our team, and he saw our paramotor propeller for the very first time, and he was asking, what's this little thingy there in the center of the prop? And we said, these are the cooling fins to provide additional cooling for the propeller. Now he literally called those fins a tumor on the profile of the propeller. He didn't like it very much. He said, this is so against any theories and ideals about how a propeller should look like. And he said, if we really need to cool the engine additionally, then we should use a fan. And this was the birth of the Darth Vader project. This is the fan that he designed, and his idea was to build a regular propeller with the ideal profile, not disrupted with anything else, to provide maximum thrust the most efficient way possible, and then add this fan to actually do what the fans is supposed to do, create additional airflow around the area of the cylinder and the head of the engine. So when we assembled these two, so the main propeller like this and the fan across, I love the design, how it looked, but it didn't perform any better. It provided the same cooling, but it wasn't better in terms of peak thrust or fuel economy. I can only explain this by the fact that the useless part of the prop are the tips. The tips are where the prop is generating vortices. Again, if you would like more detailed explanation on this, refer to the video in the paramotor geometry classroom where I explain the physics, what happens at the tip. So the tips are useless. The tips only generate vortices and drag and actually harm the overall performance. And with the Darth Vader propeller, we actually had 4 tips. So whatever efficiency we gained with a clean propeller profile, we lost with adding 2 additional tips to the equation. We didn't give up. And I have huge respect for the passion of Dusan and Milos, our propeller guys, and that they kept searching and researching and trying to find a better propeller. So the next what they came up with was the Sikorsky project. That's the working name, the working title, because it actually uses a helicopter profile. And it may sound weird, but in the aviation theory, we are flying so slow that we are actually closer to hovering than flying in terms of big airplanes. So he decided to use the helicopter profile, and he calculated that the ideal pitch would be much higher, not 10 degrees, but maybe 15 degrees, and he came up with this propeller. Again, huge investment, time in doing all the calculations and machining the mold, manufacturing the blade, and nothing happened. I was so excited to see it because it just looks so amazing. It's such a beautiful piece of engineering, so beautiful, so thin. So there's a very long chord length, but very low height of the profile. It's so beautiful, and I had high expectations, but it didn't deliver more thrust and it didn't deliver better fuel economy. So it's another project to put on the shelf. The next project in line was the blade project. It reminds me of a sword. Again, a very beautiful thin profile. I love it very much. And it's slightly shorter chord than the previous one because that one wasn't revving very well. So we needed to unload the engine a little bit. Again, that was a misunderstanding that we actually thought we are having 25 horsepower at 8,600, which we are not. So that caused some wrong calculations on that propeller. So we ended up modifying that profile, making a slightly shorter chord, and Milos and Dusan designed this beautiful propeller. It was doing well, but not better. So when I say it's kind of a failure in this research and development, I only mean that it wasn't performing better, although we expected it to perform better. Same fuel economy, same maximum thrust. Now, when I refer to maximum thrust, I don't measure thrust on the ground. I don't care about the static thrust. I don't think it's a relevant number. What I do is I simply measure how many seconds it takes to climb 100 meters. I'm using the same glider every time, so that measurement is very accurate. It wasn't any faster. So the differences between propellers were like 29 seconds instead of 31. So yes, you may say it's an improvement, but the improvement is so small that, well, we expected better. And if the difference is 5%, it could be measurement error, but overall it's not a revolution. It's just what it is. So the blade goes onto the shelf. So Dusan and Milos did not give up. They just continued. So they came with an idea that they really believe that we should not be flying at 9.5 degrees of pitch. angle measured at 75% of the prop diameter. They believe that ideal, based on the textbooks and the theory and so on, would be around 15. So they came up with the needle. This propeller is a propeller for the Master. It may look like one from an Atom 80 or some 10-15 horsepower engine, but this is a prop for 25 horsepower Master. Although there's so little propeller there, but so the chord length is 1/3 shorter, is 30% shorter, but the pitch is 15 degrees instead of the usual 10. So the concept here is increasing the pitch. Of course, you cannot change just one thing. You need to, if you increase the pitch, you need to reduce something else. So we reduce the chord length. When I did the first measurements, I was so excited about the propeller. My climb rate was 20% better. Literally, I climbed 100 meters in a 20% shorter time. I thought this will be the next revolution, and obviously it wasn't. And I repeated the measurements, and it seems like I did something wrong. And because later when I repeated the measurements, the values were pretty much the same. It was slightly better than a regular prop, but not that much better. So although the prop looks really, really cool and very extraordinary and exceptional, it didn't perform significantly better. Again, we failed to make a breakthrough in the propeller design, but it looks cool, doesn't it? Maybe the Variomatic got it all wrong. The Atom 80 is spinning the prop 2,500 RPM. The Master is spinning the prop at 3,200 RPM, and the Cosmos is down to 2,500 again. So is the Polini 303, 250 and 130 and many other engines. Seems like most of them are spinning the prop at 2,500 RPM, except the Master, which is over 3,000, and many similar engines like that. So why the difference? I'm no expert in propellers, but I asked my expert Dusan and Milos about their opinion, and they said it's wrong. At 3,200 RPM, at this diameter, the tip of the propeller is spinning at very high speed, 0.65 of the speed of sound. Now, based on aerodynamics, textbooks and theory, the ideal propeller speed would be around 0.5 of the speed of sound at the tip, which corresponds surprisingly to 2,500. They said that if the Master would be spinning the prop slower, we would design a different propeller for that, but it would be more efficient, and most of all, it would be more quiet. Now, I didn't find the answer to the question why the Master is spinning the prop so fast, so I figured out that we would eventually try ourselves. Now, this is not a standard Master. This is a very unique, one and only in the whole world Master that we modified to spin the propeller at 2,500 RPM at the 8,600 RPM on the engine. So what we did is we replaced the pulley. This is the original one, and this is a new one. It's custom built. I've designed this pulley, I had it machined. We also needed to make a new eccentric, and we replaced the bottom pulley with the one from the factory R, which is slightly smaller. So overall, we got a 3.45 reduction ratio instead of 2.68. When the engine is revving 8,600 at full power, the prop will be spinning only 2,500 RPM. Now, obviously, you cannot put just a regular prop on this engine. Recall the equation from the beginning of the video. If you cannot just change one thing. If you would put just a regular propeller on this reduction ratio, it would be spinning slower. That means it would not put sufficient load on the engine, and it would not stop the engine at 8,600. It would rev God knows how high, and it would eventually damage the engine. So let's have a look at the numbers. So here's the chart of the three measurements I did. The first is with a 3.45 reduction ratio with this propeller, and the second was with 3.45 reduction ratio with this propeller, and the third one is standard. As you can see, there was not a big difference. With a 3.45 reduction ratio, the noise level was 107 decibels point something in both cases, and it was 109 point something with a standard reduction ratio and standard prop. Now, this may not seem to be much, 107 compared to 109, but the decibel scale is not linear. It's pretty big difference in terms of sound energy, but I have to admit, it didn't feel much. There was no such things like, wow, this is so quiet, or anything like that. Even guys standing by, it's like, no, you couldn't really perceive the difference. It was a measurable difference, but to a human ear, sound was different, the pitch of the sound is different, and so on, but overall it didn't feel like, wow, this is an amazing improvement. Now let's have a look at the sound at level flight. In my case, level flight is 5,500 RPM, and in order to do a proper measurements, I did a setup on my field where there's a road. I would be foot dragging the road, which means I'm constantly more or less at level flight, right? There might be minor oscillations. And because there are minor oscillations, I did 6 rounds with every propeller. I placed the sound meter on the tripod, didn't move it, so I think the measurements is pretty accurate. It doesn't measure the sound that I'm perceiving as a pilot, it measures the sound as a bystander, let's say. Why I didn't measure, I didn't hold the noise meter, the sound meter here in my hand while I'm flying, because it's extremely sensitive where I'm placing it, and I want it to be comparable for both tests. That's why I'm foot dragging the road from at an equal distance from the tripod with the sound meter. Let's have a look at the numbers. So I did 2 rounds. I did that with this propeller. So I did 2 rounds, and you see the chart, the blue line being the 3.45 and the orange line being the 2.68 reduction, and I see no difference. Me as a pilot, I couldn't perceive any significant difference in the sound of both. Bystanders, I asked the bystanders, was it quieter? I was like, no, felt the same. So this is really surprising, because Dusan and Milos, my propeller experts, were very confident it will be a lot quieter. And maybe it is, but with just minor difference. It's just not enough to justify all the hassle we had with building the 3.45 reduction ratio and all the propellers and everything, so that was kind of a disappointment. Yet I wanted to finish the experiment and in the last test, and that is measuring the fuel consumption. So my standard setup that I use a 1 liter bottle. I climb, and once I reach my level flight altitude, which is usually 400-500 meters, I switch so that the fuel is not being sucked from the main tank, but only from this additional bottle. Is exactly 1 liter, and I measure the time with the stopwatch, how long it takes for engine to burn 1 liter, cruising at the same altitude, not touching the brakes, just gently big circles. And well, 12 minutes and 52 seconds, that corresponds to 4.66 liters per hour. That was another big disappointment. I normally fly on a long-term average at 4.3. Now there might be differences how this carburetor was adjusted and so on, but in general it was no better. It was actually maybe even worse. Now you may argue that maybe these are not the optimal propellers for that, we just improvised with whatever we had on the shelf. But I would disagree. These are pretty good profiles and they seem to run fine. I don't think that improving anything on the propellers would would make such a significant change to justify this thing. So we invested a lot of effort and time and money into this experiment, and it did not confirm what the theory predicted. It wasn't quieter at full power, it wasn't quieter at cruise RPM, and it did not burn less fuel at cruise. So, suck it up. So what comes next? Honestly, I believe we tried pretty much everything, and at least from my perspective, seems like this is the end of our journey with the classic design of propellers. We tried different blades with different profiles, different pitch, different chord length, different RPMs, pretty much everything what you can do with a fixed pitch prop, and the differences were just not relevant, not sufficient to call them an innovation. There could be some other options though. We were considering putting winglets on the propeller, but Dusan and Milos say that they wouldn't expect true benefits from adding the winglets, and I'm unaware of anyone trying proper winglets. I've seen some minor, like 5-10 millimeter winglets on propellers, but that doesn't really count. But true winglets I haven't seen on any paramotor prop so far, and in fact I haven't seen true winglets on any other prop so far, and I'm quite certain someone has tried already for big airplanes like Rotax engines and so on. It seems like this, even theoretically, this is not likely to bring true benefits. Now, ducting the prop had two major problems. First of all, they were performing the study with a really shitty prop. It wasn't really a real prop, a profile. It was just a sheet metal twisted and at a specific angle. So they improved the performance of a really bad prop. Secondly, well, they did it in a smaller scale, but if you would upscale that to our perspective, to the size of a paramotor, then the whole duct would need to be about 50 centimeters long, about 15 to 20 centimeters thick, and the gap between the prop tip and the inside of the tunnel would need to be less than 5 millimeters. Now, honestly, I don't see how these dimensions and this mass would be any way possible in the world of paramotoring, like carrying such a huge and bulky duct around the propeller, and of course the tiny little gap. That's just ridiculous with our engines vibrating and flexing on the rubber mounts so much. Ducting a fan could be possible at smaller diameters, maybe for electric, but the theory says a larger prop is always more efficient than a ducted small one. So I still believe we need to stay within the 130-140 centimeters diameter. So as for now, I'm not going to experiment with winglets, and we're not going to experiment with a ducted fan so far. Another very interesting concept that caught my attention was the toroidal prop developed by MIT. I think it was a year or two ago. Sounds amazing, really sounds amazing. It's possible to do. It's just so far the toroidal props were implemented for boats and drones because simply of the small diameter. At the big scale, it would be very, very challenging to build such propeller. It would be extremely expensive, effectively not repairable, and you would end up with a very, very expensive propeller that would be just one-time use. You hit a stone and you break it. So maybe in the future we'll experiment with that when we find a suitable way of production. But for the moment, yeah, if anyone dares to make it, please let me know about your results. I'm really excited, but I doubt we will see toroidal props in the near future in paramotoring. I promised you 10 experiments, and after mentioning 8, I said this might be the end of our journey with classic propeller design. I owe you 2 more. This is number 9, the Variomatic propeller. Now, the Variomatic propeller is the first in-flight adjustable propeller for paramotors. It's effectively like two propellers in one. When at cruise RPM in the mid-range, you have the prop set to high pitch, which reduces the RPM you need for level flight, and it reduces the fuel consumption by 33% compared to a normal one. Then when you add throttle, this blade will rotate around the bearings inside the hub, reducing the pitch of the prop, allowing the engine to rev up all the way to 8,600 and reach the full power. So effectively you have like two propellers in one, high pitch for cruise and low pitch for peak power, although the transition is smooth and seamless. The only downside of the prop is slower acceleration, so it takes probably twice as long for the prop to rev up from 5,000 to 8,600 on the engine. But acceleration is rarely a priority for cross-country flights. So I call this a great success. Finally, after all the research and development projects we did, this is finally a big success, and it delivers 33% longer flights. Combining this with the electronic fuel injection recently introduced by Variomatic, that would be amazing. And the EFI reduces fuel consumption by 30-40%. This reduces fuel consumption by 30-40%. Now combining these two, that would be the holy grail of paramotor efficiency. Let's hope it's gonna happen. The number 10 is this black leading edge. This is a rubbery material. It's not actual rubber, but it's relatively soft and flexible, so it can absorb the energy of an impact of a stone and release it again. So the stones just bounce off the leading edge without the leading edge cracking. It doesn't improve efficiency, it doesn't give you more thrust and better climb rate, but it definitely increases the durability of the propeller. We have introduced this leading edge on our Variomatic propellers, but we are now implementing this rubbery leading edge on our regular propellers as well. Really good combination. So this was something like a tour through a museum of our research projects in the territory of paramotor propellers. Most of them were failures, but we eventually succeeded. I want to ask you for your support, so we can fail again. If you like this video, please hit the like button, share it, add some comments, and if you would like to support us even further, it's a very easy solution. Next time, when you're purchasing paramotor gear, please consider a scout. Thank you very much, and see you soon.